Yeah, so in today's session, we're going to look at, as I promised, graphs of derivatives. And this is quite an important topic, I should say. And I'm going to start with really the conceptual part of it so that you actually get and figure out and understand in full really what we mean when we talk about a graph of a derivative. And notably, we're going to notice the difference, or rather the similarities or the relationship, the connection that is there between a cubic function, its derivative, as well as what you call the second derivative. Yes, correct. We're going to create that link. And after that, then I'll spend some time talking around questions that deal with the nature of roots, which is a concept you would have done in grade 11, but we'll just have a recap of that. So I'm going to start by uh, um, typing in a function, f of x. So let's call this one f of x. And we want this to be a cubic function. So I'm going to create one here, and I hope I create a good one. So 2x cubed minus 3x squared plus 4x. I don't know if this graph even is going to give me a nice shape. It's not. Let's just make that. Okay, this one is not that terrible. What just makes it terrible is the points of intersections, but that's okay. We've got not the points of intersections, the turning points, but we will get through that. It's okay. We know how to. I mean, why am I saying turning points? I want to say the intercepts. Yeah, the intercepts are what kind of makes it look really bad. But let me find a nicer one. Negative 3x cubed. Yeah, maybe let's take this one. Negative 3x cubed. And what else do I have? Plus 15x squared. So maybe this one will look nice. And then yeah, let's take this one. Yeah, this one looks decent. I think we can do with this one. Let's just do that. It's going to be quite important to note a few things here. Right. So this is a cubic graph, guys. This is how a cubic graph would look like. In this case, it is not surprising that it is decreasing. I hope you note it is simply because the coefficient of the cubed term, which is a in this case, is negative. We have already established in our previous sessions that if a is negative, it's decreasing. If a is positive, it is increasing. Now, I'm going to sketch through this software, and this is just to save time. I'm going to sketch the graph of the derivative. And I want you to be careful and note this deliberately, that if we find the graph of the derivative, so watch this. You need to be aware of this. So we've got f of x is equal to negative 3x cubed. I don't know if that was a 15x squared minus 21x plus 9. I hope that's what it was, at least for the record. Yes, it is. So I want you to be aware of the fact that if I take the first derivative here, it gives me a negative 3 times 3 is a 9, right? So it gives me a negative 9x squared plus a 30x minus 21. So take note that this here is actually a cubic function. This here is a parabola, or if you like, you may say a quadratic. This here is a quadratic. And if I take the second derivative, watch this now. It is a negative 18x plus a 13. That's what it becomes. So it is very important that we note these relationships. So the same cubic function can get you a parabola, and that can get you a straight line. Now, I want us to see how this looks like graphically so that we can now start creating connections. So I'm going to ask GeoGebra to sketch for me here f prime. I'm going to ask GeoGebra to sketch for me here f prime. Where is my prime symbol? Here it is. There's the parabola. Here's the parabola that has been sketched. So that's the derivative. And of course, it should make sense for this to have a set face. It should make sense for it to have a set face because it is minus 9x squared. So again, the negative. I hope we're connecting the theory here. Now, I'm going to ask GeoGebra again to sketch for me f double prime. Which is a straight line. And there's a straight line with a negative gradient. It is decreasing. Now, it is time that we actually zoom in and see what exactly is happening. And for us to do that, I'm going to show you a few things. I'm going to focus on the turning points of the cubic function. I'm going to focus on those turning points. And I will also focus on the turning point of the parabola. I must not neglect that. There it is. Right. Now, maybe let's take this to open board so that we can freely discuss. Great, here we are. Now, this is the long and the short of it all, and this is what I need you all to understand. You see, your cubic function has two turning points, one at A and the other at B. And what we need you to know and be aware of is the fact that the x value of that coordinate at B will become the x-intercept of the parabola or of the derivative. So the green is the graph of f, the red is f prime, and the purple or the blue is f double prime. So the first fact I want you to be aware of is that the x coordinates, and I'm very specific and I need you to capture this so that you differentiate. The x coordinates of the turning points of the cubic will become the x-intercepts of the derivative. So please be aware of that. Whatever the x-coordinate is at B, which is a turning point, that must be your x-coordinate at C, which is an x-intercept of the parabola. And I think this picture is actually quite clear at point A, as we can see A is not just the x coordinate, is not just a turning point actually. A is also an intercept of the red one, or the derivative. So this is a very important fact, and you will see I've got a question that we're going to tackle which actually addresses this concept. Then another important thing that I need you to note is that the turning point of the parabola, which is point D, that x coordinate of the parabola is actually the x coordinate of the straight line. Now, let me add on to your understanding the fact that the midpoint of these two intercepts of the parabola will actually give you the x coordinate at E. So if you take whatever the x value is at A and you add whatever the x value is at this point C here, and you divide by 2, that will give you the x value at E. Now, there is a special name for the x value at E in terms of the cubic function. That x value at E is, if you'll recall, is what we call the point of inflection. And it has to make sense because remember, when we look for the point of inflection, we actually take the second derivative and equate it to 0. When we look for the point of inflection, we take the second derivative, we equate it to 0. And practically speaking, your second derivative is essentially a straight line equation. So when you take the straight line equation and equate it to 0, you are literally finding the x-intercept of that straight line. And it has to make sense then why that x-intercept of the straight line is the x-coordinate of the point of inflection. I hope we're together there up to that part at least. So this is quite key, very, very key for us to note and understand. Now, why? Look at this question here. You see in this question, you are given the graphs of the derivative. You see G prime. So if you are given G prime, it means there was a G of X, which you can imagine was something like AX cubed plus a BX squared plus a CX plus some constant D. So we are given the graph of the derivative, which is a parabola. And I want you to note again that this parabola is actually a parabola, a happy face type of parabola, very much happy, which means our cubic graph should actually be increasing. In other words, A is positive in the cubic. So it's quite important to note that. If this parabola was a sad face, like in the example, the illustration that I gave, then we know our cubic would be decreasing. So it is important to note that the happy parabola as a derivative implies or says to you your cubic is actually an increasing function. Now, another thing to note, as I have already mentioned, is the intercepts. Maybe let me not get ahead of myself here, and let's read together so that you also see how I pick these things up. I did not finish reading. We just read about the derivative. Another thing that's given is the straight line. Now, they are even telling you, in case you missed it, they are telling you that the graph of g of x is the derivative of a cubic function g. Then furthermore, we are told that the graphs of h and the derivative have a common y-intercept at point E. This is a deliberate statement which you have to understand, okay, because it does give you some key information. And that key piece of information is that since you have the full equation for the straight line, and they're telling you there's a common y-intercept, it means you must know that there is a -4 at point E. And that -4, as a result, I hope you note, it gives you the value of c for the parabola, because it is the c, in this case, is the y-intercept of the parabola. And then furthermore, c and d are the x-intercepts of the parabola, which is the derivative. Now remember what we said. The x-intercepts of the parabola actually give you the x-coordinates of the turning point of the actual graph of G. So it's very important to remember that relationship. Then point A is the x-intercept of H. Now listen to this. Point A is the x-intercept of H. H is the straight line, right? And listen to this. Point B is the turning point of the parabola. Now, line AB is parallel to the y-axis. What is this saying to you? It is saying to you the x-coordinate at A is the same as the x-coordinate at B. And if the x-coordinate at A is the same as the x-coordinate at B, this is just another way of saying you have a point of inflection. They have given you a point of inflection for the cubic. All right? Of which then we could argue, you and I could argue then that no makanjani here, this straight line somehow should be related to the second derivative. And how is it related to the second derivative? It will give us the x value, at least the x value of the point of inflection. So that's why it is very important that we actually note this relationship between the cubic, its derivative, and the second derivative. All right, it's time to get to the questions. Let's answer them. And guess what? Look at the first question. Already by looking at the first question, we have answered it in our sketch. You see, and the question says write down, meaning you don't have to think about this. 0 and -4, 1 mark for free. Determine the equation of the graph of G prime, the graph of the derivative, in other words, in the form ax squared plus bx plus c. So as I have said, we kind of have the value of c already. There's two ways to do this, by the way, but I'm just going to use the simultaneous route. It seems quite easy for me because I already know that I've got ax squared plus bx minus 4. So I might as well create two equations and solve for a and b simultaneously. And I'm going to create those two equations by using the intercepts. So here y will have to be 0 when x is a -2. That's my first equation, and I can clean up a little bit and here and simplify it. So that's a -2, sorry, that's squared. Hey, very, very serious mistake there. So that becomes a positive 4a minus a 2b minus a 4. And instead of writing it as minus a 4, I could just say equals to 4. I hope you see what I'm doing there. Then I'm going to substitute the other x-intercept, which is the point D. Again, when y is 0 there, x has to be a 6. My word, 6 squared is a 36. And again, I'll say 4 is equal to 36a plus a 6b. And at this stage, you have two options. You can use elimination or substitution. I don't know which one you want to use. It's really up to you. But I guess you probably like this thing called substitution because that's what you often do when you solve simultaneously. So from equation 1, I'm actually going to make b the subject of the formula there. And I hope you'll agree with me that in making b the subject of the formula, I will eventually divide by 2. And then so it will become 2a minus a 2. That's what b will become. And then I will substitute into the green equation. So where I see a b, I will put in a 2a minus 2. This is 36a, and that's a 12a, and with a minus 12, that's a 4, so that's a 16, and that's a 48a. All right. So is there someone who's happy to do 16 over 48? It's a Sunday. I don't trust my arithmetic actually. 16, 32. Yeah, 16 times 2 is a 32, right? Oh, so it looks like it's a third. Yeah, it's a third. Great, thank you, Lube. It's a third. So now I can find B. So B will be 2 into a third minus 2, which is 2 over 3 minus a 2. That will be 2 minus 6. I guess that's minus 4 over 3. Am I right there? You can double check that for me as well. So those will be then the values of A and B. I'm hoping that my simultaneous equation here has been okay, and that I have not broken any rules. So finally then the equation will be y is equal to 1 over 3 x squared minus 4 over 3 x, and then we have already established c is a negative 4. So that's that. Now write down the coordinates of the turning point of G. Okay, so as I said, you can easily get the x coordinate here by just finding the x value at A. So I'm using that because the equation for A is quite simple. It's a 2x minus 4. So when we find the x-intercept, obviously we equate that to 0. So x becomes a 2. So the x value at B is a 2. Now, your job is to substitute that 2 into this newly found equation. So, Lube, please, may I ask that you do that for us? You substitute a 2 into this equation, 1 over 3x squared minus 4 over 3x minus 4. Right, thank you, Lube. Negative 16 over 3. And it does make sense because surely it is in the negative y-axis. Great, awesome. And guess what? The x-coordinate of the point of inflection of the graph, we have it already. We have it already. So that x-coordinate is a 2. So for the point of inflection, which is 1 free mark. So yeah, this is one exam type of question to test the skill which we have been discussing. Now, the next important element that I want to discuss for the remainder of today's lesson is nature of roots. Now, where does this concept come from? And I want to go back a little bit to grade 11. In grade 11, you worked with the equation ax squared plus bx plus c equals to 0, and then you completed the square and discovered the quadratic formula that, oh, instead of factorizing, there is a sort of a systematic way of actually calculating the roots. That's what you discovered. And this today is freely given even in your information sheet. Now, the next thing that I need you to understand, right, is that we said this thing here, we called this thing the discriminant, and we use delta to represent that. This thing here called b squared minus 4ac can actually help you to describe the nature of roots. And this is what we said. We said there are two main categories. You can have roots as real or non-real. That's what we said. And then we said for non-real is very simple. We just need that delta thing to be negative. So in other words, you type in a b squared minus 4ac and you get a negative number. You already know roots are non-real. Then we said, well, in a situation where roots are real, then we can actually have a situation where they can be rational or irrational. But we can also actually have a situation where they are equal or non-equal. All right. So I will talk about that as well. So if they are rational, it means that delta is a perfect square, because think about it. If you are solving here, then let's say minus b, we get a minus 2 plus something over a 3, whatever the situation is. So the only way you can be able to add a negative 2 to a square root of something is if that something inside the square root is a perfect number. That's it. So that's then when we said, okay, if delta is a perfect square, if delta is a perfect square or is a square number, then the roots will be rational. But the roots will be irrational if delta is not a square number. And then we spoke about equal and non-equal. Some people would say, instead of saying equal, they will say it's a double root. Some will say, instead of equal, they will say non-distinct. So I'm just sharing with you that these are just synonyms. Of course, the opposite is also true. So distinct would mean non-equal. Distinct means different. So non-equal, and or unequal if they don't want to say non-equal. Right. Now, when are they equal? Well, they are equal if delta is exactly 0. And they are not equal if delta is bigger than 0. So it's very important to understand this. Now, it is extremely important. Beyond this understanding, it is crucial that you actually understand the visual representation of this equal, non-equal story, the graphical representation. And that's what I want to bring to your attention. You see, here's an illustration of roots that are non-equal or equal. By the way, graphically, I'm drawing the parabola as well because this all comes from the quadratic, right? So as you can see, the roots, by the way, refer to the x-intercepts in this instance. So as you can see, in this case, I've got an x-intercept on the negative x-axis and an x-intercept of the positive x-axis. So this is definitely a situation where delta is bigger than 0 because the roots are different. Whether they are rational or irrational, it doesn't matter at this stage. And of course, there are many cases as well. Then here's another one. And this is exactly the situation where roots are equal and delta is 0. On the other hand, a situation where roots are non-equal is when you actually have a parabola that does not at all touch the x-axis. There are many instances, of course. I've just drawn the 2 yellow ones. That's your non-real situation. Now, if you get what I'm saying, right, I want to bring to your attention a question of this nature here. So fortunately, we have sketched this graph. I hope you still remember how to find intercepts, factor theorem there, coordinates of the turning point, find the first derivative, solve for x, sketch, in clearly indicating the intercepts which you found in 8.1, and then the turning points which you found in 8.2. This graph I've already sketched actually because it is what we were using as our illustration. But I want us to focus on the two questions 8.4, which are asking basically about the values of x for which the gradient is positive and the values of k for which f of x equals to k will have exactly three different real roots. You see that question of roots is there. So I would like to deal with this. This is where students lose marks, and it pains me when students lose marks on such easy matters. So please pay attention now, because this, what I'm about to say, is what will bring your nightmares to an end. Right, so here's my graph. I'm gonna take a screenshot of this, put it there so that we can answer the questions properly. So let's do this. Right, so we have the sketch and everything, and we have the marks for that. Okay, right, there's our sketch. Now, I'm going to show you, I'm going to start with this one first, where it says for which values of thingy is the graph increasing, or is the gradient positive. By the way, remember what I said when we spoke about the first derivative, guys. I said when you see the first derivative, you got to think of the gradient. Now, I've got a very nice friend of mine called the Slope Man, and I always introduce students to this guy because I find him to really work out things wonderfully. Very great stuff. So watch this now. I'm going to introduce you to the Slope Man. It's something that you know, but maybe you have not thought of. So start thinking about it from today. Very helpful tool. Here it is. This is just a summary of the straight line. You get four types of straight lines. You get a straight line with a positive gradient, and that straight line will always be increasing. You also get a straight line with a negative gradient, and that straight line will be decreasing. You also get a straight line which is vertical. Sometimes they will say it is parallel to the y-axis. Sometimes they will say it is perpendicular to the x-axis. The point is, for such a straight line, the gradient is undefined. And lastly, you get a straight line which is horizontal. Another thanks for notifying me about being muted. That thing again off, the microphone switching off. So thank you. Where did I lose you? Was I talking about the slope man already? Was I done? Where was I, Lube, when I cut? Are you there, guys? Can you hear me now?
You're still explaining, so when it's zero or yes, sir.
Okay, I was still on the slope, man. Yeah. So these are the four
Please.
types of lines that you get, and I want to show you why these are helpful when it comes to our cubic graphs. So you see this green graph here. I'm gonna draw the different lines from the slope, man, and I'm gonna draw these in red. See, I'm gonna draw a line there. According to the slope, man, because this line is decreasing, the gradient is negative. I'm also gonna draw a line here. According to the slope, man, there, the gradient is actually 0. I'm gonna draw another one here. And according to the slope, man, the gradient is actually positive.
Decreasing.
Yes,
Increasing.
increasing. Yeah. And then I'm gonna draw another one there. At the turning point, the gradient is 0. And I'm gonna draw another one. The gradient is negative. That thing is decreasing. Now, the question here is asking, for which values of x is the gradient positive? And here is the positive gradient. So surely it is between point A and that point B. In other words, it's between the two turning points. So of course, you have sketched and you have your turning points. So in this case, you got to answer in context and say, well, if x is between a 1 and I don't know what that x value at B is, but it's surely a 2 point something. Let's argue 2.3. So then you'll say that, and of course, there's currently a debate whether we're going to increase, whether we include the turning points or not. You will get a mark. That is the settlement. They have agreed. Whether you include them or not, you'll get the mark. So that's that. If you can just always use the slope, man, I promise you, you will never struggle with this type of questions. I hope you can see right from here that for x values where the gradient is negative, you are looking at this region here and that region there. That's what you are looking at. So you'll have two answers there. You'll have two regions. You'll say x values that are less than 1 and x values that are bigger than whatever that we said is 2.3. X values that are bigger than 2.3. You can actually do this even for the parabola. Whether it's a sad face or a happy face, you can literally just draw your two straight lines there. Obviously, at the turning point is 0 gradient. Okay, even when they ask, when is the function increasing? Sometimes that's what they ask. Sometimes they don't say, when is the gradient positive or negative? Sometimes they ask, when is the function increasing? Whenever they ask, when is a function decreasing or when is a function decreasing, I promise you, just draw the straight lines, draw the slope man. Whenever the slope man is positive, then you must know your function is increasing. Whenever your slope man is negative, then you must know your function is decreasing. I must actually show you that even with the parabola and hyperbola, I know I've seen these questions being asked. Look at this. Let's argue I've got a hyperbola here. I just want to show you how this also helps with your functions. Let's say that's a 2. And let's say this here is a 1. And maybe our hyperbola for today goes in the second quadrant and the fourth quadrant, like that. You see, if I draw the gradient, if I do the gradient test, surely, look, I can draw even number of straight lines like that. I can do that. I can do that. And I hope you can see that actually all these are increasing. All these are increasing. Because that's what the slope man says. Increasing, decreasing, undefined, 0. So as long as they are going up, they are increasing. If I had a hyperbola in the second and the fourth quadrant, I mean the first and the third, sorry. If I had it in the first and the third, I could also draw those straight lines like that. there. And surely look at that, look at that, look at that, look at that. Decreasing, decreasing. So that's how you can actually check whether a function is increasing or decreasing, by simply doing a gradient test or a straight line test. All right. Now, let's get to the final part, which is this question here. Values of k for which f of k will have exactly 3 different real roots. Now, I want you to think of k as a horizontal line. The horizontal line y equals to k. And I want to show you how that line actually looks like. So I'm going to sketch here the horizontal line. I hope this will allow me. The horizontal line y is equal to k. I want you to see how exactly it looks like. There is the horizontal line y equals to k. Now, of course, k is a slider, and I'm gonna just adjust the settings for this slider so that the minimum is not a -5, but rather I would have it at, I'd rather have it at a -10, something like that, so that we actually have much leverage, and you can see what's going on here. So I'm gonna have it at -10, and after this, you guys are never ever gonna struggle with this type of questions, because really they're easy. -10, let's make this one a 10. Yeah, so you see the line equals to k. It's a horizontal line, and I'm gonna play the slider k. I'm gonna play the slider k, and you will see it's gonna move up and down. It's gonna move up and down. So watch this. And obviously it will move between 10 and -10. Currently it's at 1. So you see it's moving up and down. It's gonna move up to 10, it will bounce back, and it's gonna move down to -10, and it will bounce back. Now, I'm gonna pause it, and I want you to think with me here, because there's something important to note. I want you to note right now that this slider is touching the point, the graph exactly at one point there. If I play it like here, I think like there, I want you to note it touches the graph then at exactly 2 points. And we're going somewhere with this, so stay with me. Here, it touches the graph at exactly 2 points. And I'm gonna play it again, let it move. And I want you to see in this instance that it touches the graph at exactly 3 points. 1, 2, 3. And I'll let it play again. And I want you to note in this case, as I let it play, it continues to touch it 3 times until it reaches the turning point B. And at the turning point B, obviously, it will touch it twice. I'm trying to get it there. Okay. Yeah, well, I tried. Right at turning point B, it touches the graph twice. And beyond the turning point B, obviously, it will touch it exactly once. So the red dots will represent 1 touch, the green will represent 3 touches, and the blue will represent 2 touches. And I hope we all agree that there's a range for this. In fact, what is quite interesting to note, what is quite interesting to note is the fact that the green for the green zone, I mean, not the green zone. In fact, the red zone, once the line goes below the red, this blue dots here, and it goes down, it will always touch the graph once. Same thing here. Once it goes out of the blue, it will touch this thing once. But it only gets to the blue zone once. And it's on the y-axis or at the turning points there and there as well. In this case, by the way, it's not always the case that it's like this, all right? It is this particular case. Then the green zone, I want you to note the green zone where it touches it 3 times is actually this region here. That's that region. Now, when the question says determine values of k for which the line f of x equals to k will have exactly 3 different roots, or for which this f of x equals to k will have 3 different real roots. It is literally asking you, how should this black line that we have been moving, this line, where should it move? Of course, vertically up and down. Where should it move such that whenever it moves, it will touch the green graph 3 times? And I hope you agree with me and you will make sense of this, that it literally has to move between the 2 turning points. So because obviously in your sketching, you would have figured out the actual turning points, the actual coordinates of the turning point. And you know by now that this is the line y equals to k. You then have to specify a region for the values of k and say, well, if k is between the 2y values of the turning points, not exactly equal to, just between, then there will always be 3 points of intersections. I could change the question and say, what will be the values of k for which the graph or the equation f of x equals to k will have 2 roots? If I ask for 2 roots, then I'm simply asking you to give me the y value of the turning point, because in this case, the y value of the turning point ensures that indeed the graph is, k touches the graph at the turning point B, but also at another point there. So there are 2 solutions actually in this one. You will get the line y is equal to the turning point at point B, the y value of the turning point at point B, and you'll get y is equal to, well, in this case, it is 0. We can all see that. So y is equal to 0 is definitely going to be one of your solutions for 2 roots, if they're asking for 2 roots. If they're asking for 1 root, then surely you want the line y equals to k to move now below your turning point. So you want it to be less than 0. Actually, why am I saying this now? So you will say k, not y, but you'll say k is 0. And here for 1 root, you will say k must be less than 0, or k must be bigger than whatever the y value at B is, the y value at the turning point is. Now, of course, this is unique to this graph. You could get an instance where you have a graph like this, and I'll show you. You could have a graph like that, right? This is actually pretty much the same thing. I wanted to draw a slightly different graph like this. Yeah, like that. Like that, yes. That's what I wanted to draw. So you see, this one is slightly different. So you seriously need to apply your minds here, guys. You need to apply your minds and actually answer according to context. Sometimes they can actually even give you a parabola like that and say, for which values of x will the line f, will the equation f of x equals to k have 2 roots, etc. So again, I need you to see that 2 roots in this case will exist as long as this line moves below the turning point. Sometimes they may ask non-real roots. it means it must move above the turning point. If they ask equal roots or exactly one root, then the line must move exactly at the turning point. All right. So that is the long and the short of it, guys. It's a conceptual thing, but I thought I should share this with you because it's quite important. And having shared this, you should be now in a position to answer all questions on calculus from rules of differentiation to sketching graphs. The only section maybe that you would not be able to answer now is the optimization. In other words, the application where they talk about minimum, maximum, etc. But that is definitely coming up in the next session, which is next Sunday. I'll definitely touch on that. I'll actually bring different problems and just show you how to work around that. It's actually not a difficult section. It's just a matter of, interpreting the statements to formulate an equation, and then you work around your minimum and maximum and all that. But for now, this will do for today. Just go and try and see if you can now answer the difficult questions around this calculus section. Thanks for tuning in, guys. Keep well. See you next week.
Bye bye, sir.
All right. Cheers. Bye-bye, Tabang.